Hello, we are the Smart Luggage team. Today's date is November 23rd. My name is Jacob Wood.
And I'm Brendan Young. And I'm Dana Louderback. This is the fall term progress update for the Smart Luggage team.
Within this presentation, we will be discussing the current status of the Smart Luggage project. Specifically, we will address the technical decisions regarding input to the system, processing, and system output. I, Jacob, will be addressing environmental sensor input and microcontrollers. Brendan will discuss user interface and video processing, and Dana will describe the drive setup of the Smart Luggage system.
Creating an autonomous luggage system requires a capable level of environmental sensing. The finished product should not damage itself or others during typical use. To accomplish the task of object detection, our team has chosen the Ping Echo ultrasonic sensor. This ultrasonic sensor topology depicted below is capable of sensing objects within 2 centimeters and up to 3 meters away from the device. Our team is also in the early stages of selecting infrared sensors to be used as a means of detecting sharp edges that the smart luggage could potentially fall down, such as curbs or steps. The environmental information received by these sensors will interface with the central controlling unit to be translated into action by the smart luggage device.
The user interface will take form of an Android app that will be developed on Android Studio. This app will connect the user's smartphone to the smart luggage via Bluetooth and will send accelerometer and compass data back to the luggage to be processed. It will also notify the user if the luggage is too far or if the luggage loses sight of the user. Currently, our time and efforts are being spent on understanding the basics of Android Studio and app development in general. In order to implement the user tracking feature of the Smart Luggage, we intend to utilize the OpenCV library in our C program. As a group, we have decided to use the second latest OpenCV version, which is 2.4.13, because it is more reliable and stable compared to the latest version. In our first prototype code, we implemented functions that enabled us to track any color by adjusting the hue saturation value trackbar as shown in the image. As of this moment, we are exploring different functions that will enable us to detect and track different objects of different shapes. Ultimately, we want to be able to track the user by shape and color with the greatest accuracy.
To translate environmental data into actions, our team has chosen the Raspberry Pi 3 to be implemented as a microcontroller and image processing unit. The Raspberry Pi 3 is ideal for our purposes due to its ability to be interfaced with various peripheral devices. Our team will rely on the provided Raspberry Pi camera to implement target tracking as well. Additionally, the communication protocols, ADC, and PWM capabilities will allow us to drive the various functions of the Smart Luggage product.
I'm Dana Louderback, and I'll talk about the drive setup. First of all, the motor controller. The motor controller is what stands between the motors and the microcontroller. As you can see here in these interfaces, some important bits are that there are 6 bits of data from the microcontroller, 2 of which are PWM signals. There is a power input from the battery pack, and on the output is another PWM signal that has 4 modes of output. 14 volts, which would be forward, negative 14 volts, which would be in reverse, 0 volts which would be a plug braking, and a floating voltage would be coasting. We plan on building our own motor controller, and here's a preliminary design of that. On the right we see an H-bridge, which is the normal means of motor control in small applications. And on the left we see an FPGA, which controls the H-bridge. That FPGA uses data from the microcontroller and uses it to control the different gates on the H-bridge. We decided that the motor controllers should each drive a permanent magnet DC motor, each with an integrated gearbox on it. Permanent magnet motors are often used in small applications such as the Smart Luggage because they are compact and inexpensive to purchase. The integrated gearbox will allow the output shaft from the motor to spin very slowly and be connected directly to the wheel of the Smart Luggage. Also, because of precision machinery used in fabrication, the integrated gearbox will add reliability to the drivetrain. In summary, we've decided to use ultrasonic and infrared sensors, video feed, and data from the user's smartphone as input into the Raspberry Pi microcontroller. The Raspberry Pi will use the data to track the user and manipulate the in-house built motor controller and permanent magnet motors to follow them.
Moving forward, we will be purchasing parts so we can start building and testing individual blocks over the winter break. We will also be completing our block descriptions so we know how to interface each block with one another.
The content of this presentation shows the progress we've made and our readiness to progress to building the physical blocks for the Smart Luggage.